Okay, so we're gonna look at microprocessor and memory coherence. Again, these slides are from Professor Lee from Georgia Tech. We appreciate he sharing these slides. Memory hierarchy in a multiprocessor machine can have different kinds of organizations. The one on the top left, that's the first kind we may see. We have shared cache. So on the chip we have multi cores, and these cores are connected to a shared cache, for example, layer 2 cache, and these cache then connected to off-chip memory. The figure on the right, so that we have top right here, this is the bus-based shared memory, and the $sign refers to the cache. So we're talking about each processor has a private cache connect to it, and these private caches are connected to a bus, and one single memory unit is connected to the bus. So all the processors will access through its private cache then to the memory. The third one we're looking at here, bottom left, is the fully connected shared memory. What that means is, again, these processors each has its own private cache, and these private cache units are connected to an interconnection network, which is different from a bus. But the major difference is that for a bus, you can only have one conversation at a time. So there's sender and there's receiver, and you cannot have two processors sending data onto the bus. But the interconnection network, you can have multiple communication pairs as long as they do not compete for one single connection. For example, processor 1 can talk to memory unit 1, processor 2 and can talk to memory unit 2 at the same time, as long as they are not competing the same port. The figure on the bottom right, that's the distributed shared memory. The difference between this one and the fully connected shared memory is that, as you can see, the memory units are actually connected to the processor and its private cache before it's connected to the interconnection network. And this leads to a very interesting performance characteristic, because if you have a processor that tries to access memory, you're talking about two different possibilities. One possibility is to access its own memory. The other possibility is to access a remote memory through the interconnection network. The overhead or the cost of these two different memory access is different. Your own memory, of course, is shorter distance, and you will normally achieve better performance in terms of memory access latency for accessing the local memory than the remote memory.
In the third type,
Yes,
the memory units are not dedicated to a particular processor, right?
correct. They're shared. And even the figure on the right, you have these memory, they can still access each other's memory. That's why we call it shared memory. See, both of these two are shared memory. In fact, all these are shared memory. Okay? If it's not shared, we're not too concerned, because it's not going to be visible to other processors. You can do whatever you want. But when you have this shared memory, then the question of coherence comes in, because you have data in these memory units. You want to make sure that all the processors see the same data for the same location, right? Even though there may be caches here and there, but we want to have these cache coherence control mechanisms to make sure that the view of data for these processors are the same. That's the consistency. Cache coherence. We assume that closest cache level is private. So that means it's not going to be visible to other processor cores. Multiple cache lines can be present across different processor nodes. Each cache going to be accessed and updated in the unit of, well, it'll be updated in terms of cache lines. You can access any single bytes, but when you update, you can update the whole cache line. Local updates, it may lead to incoherent state, which we'll see in the example in the next slide. We talked about the cache design. We discussed write-through cache and write-back cache. Depends on whether you want to save the memory bandwidth or not. You can use write-back to save the memory bandwidth. We only write the update data to the memory once the cache line is invalidated or overwritten. For bus-based connections, which the first at the top two we saw in the previous slide, the characteristic of this bus-based interconnection is the globally visible. By that we mean if a processor sends a read request or write request to the bus, everybody's gonna see it because they are connected to the bus. So they share the control signal, they share the data signals. So every operation on the bus can be seen or is visible to all the processors, the controllers of the processors, memory controller. For point-to-point interconnect, the transaction on the bus is only visible to the communicated processor nodes. So whichever communication pair are sending data through the point-to-point interconnection, only that pair is available. It's visible. Let's look at the next slide. I think it may not show up correctly because we have an animation here. You may see different values on your handout. Let me show you the animation to help you understand. So suppose we have, let me start from the beginning. We have 3 processors and each one has a private cache, and then these caches are connected to the shared memory through this bus. And when you see drawing like this, that's a bus. If it is interconnection, we normally do a block and then have the connections. Suppose we have a memory at location X. The value is minus 100. If these 2 processors read value from the memory, first time it is a cache miss, so we will load value, and then the value minus 100 will be put into the caches. Okay. Now, this processor updates its own copy. It's a local update. Okay? It's a local update, and that most of the time cause incoherent, because this processor sees the value of this variable X is minus 100 and the other processor sees it's 505. So that's different, so that's not what we want. So next time when this processor reads the value again, if we do not have any cache coherence control, it's going to read the stale value, so it'll cause the incorrect program result. And another processor reads, do we want it to see the old value or the new value? Of course, the new value. Right? So that was the write-back protocol, because we didn't write the updated value back because there was no invalidation of the cache line. Whenever we want to flush the cache line, we'll write the value back. Right? That's the write back protocol. For write through, we still see this problem, the coherence problem. Again, we're reading the value at the beginning. After update, this processor, because it's write through, so the new value will be populated to the memory. Okay? And new processor reads, it will get a new value, but the first processor still has the old value. So that's the problem. The coherence is defined in this way. In multiprocessor is coherent if the results of any execution of a program can be reconstructed by a hypothetical serial order. Okay. So that's the definition of coherence. The implicit definition of coherence, there are two aspects: write propagation. Whenever we write, let's call it local update, we want this update to be visible to all other processors. And also write serialization. All writes to the same location are seen in the same order by all the processors. Okay. And to all the locations, in that case we'll call it write atomicity. We'll see in the next example that when we write values to this shared memory, because of the distance of the processors, how these updates are populated, it may happen that these processors will see different values at different time in different order, and that's not what we want. That's not the coherence we want to achieve.
Can we have something like this in write-through cage? Like as the processor updates to memory, it can also update the value, the updated value through the bus to all the other processors which took that value. For example, here, when this processor writes the value back to memory, it can also even write it to the processor one. Like we can have a buffer which stores all the data about which processor accessed that value.
Very good point. That's exactly the control mechanisms we will need to use to handle this coherency in a bus connection. But before we talk about the actual coherence control protocol, we have one more example. In this case, we have 4 processors. They are interconnected in this way: P0 connected to P1, P1 connected to P2, and then P2 to P3. This kind of connection, this linear connection, implies that the data will be relayed to the other processors through multiple processors. So for example, if I want to send a new value to P3 from P0, I need to go to P1, then P2, then P3. There'll be some delays. So one example we're showing here is, assume variable a and b are zeros at the beginning, and time t1, P0 updated the value of a to 1. In the same time slot, P3 updated the value of b to 2. And these two processors will try to populate the values to each other, actually to all the processors. So in T2, this new value of a reaches to P1, and same time the new value of b reaches to processor 2. In the next time slot, the new value are populated even further. So the new value of A1 now reaches, the new value of A now reaches to processor 2. Also, the new value of B now reaches processor 1. Okay. And the next cycle, in fact, should be T4. The new value is now populated to all the processors. So we will have to take multiple time slots to have the new values populated to all the processors, which means that you can see from T1, T2, T3, the processors are seeing different values, okay? And that's incoherent.
What if, like, say, for example, at time T3, P0 again updates the value of A. So in that case, propagating this information will be delayed again.
Right, so that's right. So because of this linear connection of these processors, the updating of these values will have to take multiple time units. Yeah. So we're going to look at a bus snooping protocol based on write-through cache. This is the control protocol we will look at in different bus connections. This is to solve the incoherent problem. We want to have these policies built into the controllers of caches so that these cache controllers can update their content according to these protocols. And the goal is to achieve coherent view of the data for all the processors. In this case, all the writes will be shown as a transaction on the shared bus to memory. And we're going to look at two protocols, update-based protocol and an invalidation-based protocol. This is the first protocol we're looking at. It's called bus snooping because the nature of the bus, whatever you send out on the bus, will be visible to all the units that connect to the bus. So you know which processor is write, which processor is read. And we have these processors similar as we saw in the earlier example. We have 3 processors, each has its own private cache, and we have shared memory. Right now the value of X in the memory is minus 100. In processor 1 it has minus 100, but in processor 3, the far right one, because the latest update, the new value of X is 505. When the processor updates the value, it will generate this signal on the bus to say that I'm going to do a write. Oh, by the way, because it's write through, so when it writes the cache, it will write through to the memory. So that's why you see this bus transaction. With the snooping, this write operation, this write through operation, is seen by the cache controller of the first processor. It sees this is a write to this variable X or location X, and the new value is 505. So the next step, the controller of the first processor, the cache controller, once it sees there's a write operation to address X, the new value is 505, it will generate a transaction, and this transaction will essentially update the value of location X in cache 1 to the new value 505. and that's the one you propose to do, right? So this is so-called the update-based protocol. In this case, the new value will be used to update the stale value in the cache of the processor 1. Now we're moving on to the next example. This is so-called the invalidation-based protocol. We're still assuming that we have the write-through cache. So when processor 3 writes the new value to its own cache, it will write to memory, the main memory. Okay. And the cache controller of the first processor will again see this transaction. The operation now is invalidation. It essentially saying to the cache of the first processor that the address or the variable x that you have a cache value now is invalidated. It's just telling the processor that this value is out of date. You should not use it. The actual operation is just mark that flag bits for the cache line as invalid. So next time when the first processor tries to access the value, it will cause a cache miss. And the cache miss will lead to a memory read. And a memory read will be able to supply the latest value of variable x to the first processor. That's what's showing up here. So if next time processor 1 wants to load x, it will load the value from the main memory because the cache miss. Okay. So that was the animation that shows how these controllers will actually snooping and do the update or invalidation. This slide here shows when we design such a controller, what kind of designs we will have. You can imagine that we will need to have a state machine. Right? Are you familiar with state machines? Right. So essentially, that's the main thing in logic design class. You want to have a state machine that keeps track of the current state, and the state will migrate to another new state if you have some triggering event. This is how we're going to describe this cache coherence protocols. We're looking at a simple Snoopy coherence protocol for a write-through cache with no write allocate. We have two states, valid and invalid. The way we mark this transition is we're going to have a single-ending arrow from one state to another. Like in this case, we have an arrow from invalid to valid. And on this arrow, we have a label processor read / bus read. What this means is that the left part of this label is the operation observed on the bus. Okay. So this process read, that's one we observed. And we have a transaction that's going to generate the operation going to be generated on the bus. This is to say, if we see a processor read, okay, coming from the processor, we will generate a bus read. Bus read will read the value from the memory, the main memory, and update the cache line. And after that, we will change that cache line, the state from invalid to valid. For any other reads, because it's a valid cache line, so we will not do any bus operations. By bus operation, we really mean that from the cache, we're going to either read or write to the main memory. So that's the off-chip memory access. So in this case, if it is another read, we will just stay in this state and we will not generate any bus transactions. If it is a processor write, we will generate a bus write. Because we are talking about a write through cache, every update to a cache line should be populated to the main memory. But still, we're going to keep the state to be a valid state, because that's to say that the copy we have in my cache is still a valid copy. Okay, now we have another possible state transition. And in this case, we use a dash line, arrow line to describe this state transition. And the label we put on this line is bus write slash nothing. This is to say, hey, if we see a bus write generated by other processors, okay, and if that's writing to the same address, then I will have to mark my cache line as invalid cache line. Right? That's exactly the invalidation protocol we looked at. We will invalidate my cache line to say that the copy I have is a invalid, out of date copy. And if you see a processor write, from myself, I will change this to invalid. I will generate a bus write. Now this bus write, this is the bus write that actually this. It's just seen by different controllers. For me, when I do a write, I will need to generate this bus write signal to write through my value to the memory, and that's going to be seen by other controllers on the same bus. So this is why this bus write is going to be the observed transaction. What about write back cache? Write back cache is to reduce memory bandwidth requirement, because you only update the main memory when you will need to replace this cache line. As a result, the majority of local writes are hidden behind the processor's nodes. So if you snoop, you don't really know when another processor updates its local copy. So how do we do snooping, and how do we do these state updates? Let's stop here. Let's continue this next class. We'll look at how we do this cache coherence protocol for write back caches, and also we're going to look at for we have other protocols that can improve the performance of processors when we're still maintaining the cache coherence. Okay.